Welcome to particulate model of matter. Today we're going to look at the solids, liquids and gases. So in this topic, what we are going to master are kinetic theory of matter, okay, and what it means, and then we will look at the three states of matter in particular. Okay, this topic is devoted to solids, liquids and gases, which are the three states of matter. And then we will look at the properties and behaviors of the particles when they are in solid state, and we will move on to then to liquid states. So we will look at properties and the behavior of particles in liquids. So we will attempt to understand why liquids are able to pour, and why solids are incompressible, why gases are compressible, why solids have high density and so forth. So then of course we will move on to looking at the properties and behaviors of particles in gases. Then after that we will actually understand what is happening during a change of state or state change, okay, such as melting, freezing, evaporation and so forth. And then last we will look at the heating and cooling curves of pure substances, and we will try to understand what are the important critical points that we can learn about the heating curve or cooling curve, and how to interpret the positions and what happens at that point and all that. So we will learn how to interpret a heating curve or a cooling curve of a pure substance. So particulate model of matter, let us understand how the particles in matters are arranged, right? How the packing is, their packing, their physical properties, right? Why they have low density, or they exist at low temperature and so forth. And we will also look at the behaviors, okay, such as density, the speed of the particles, etc. So these are the things that we're going to look at. And of course, before we go into that, let us recap what is kinetic theory says. Kinetic theory states a couple of things. The first thing it says is all matters are made up of particles. Okay, kinetic theory is based on the fact that everything is made up of particles, and that these particles are in continuous motion due to the internal energy they possess. So the particles do have their own energy with which they move, and this continuous motion is due to the energy that they already possess, which is what we term as internal energy. So let's look at what are the three states of matter. Matter can exist in three states, namely it can exist in the form of solid, such as your ice cubes and most of the things that you can touch and feel. Okay, they are existing as solids. And liquids are like your water, your drinks, your beverages and all that. They are liquids, they are able to pour quite easily. And then gases are something that you can only feel or experience with your skin, okay, or you can smell or whatsoever, but it is very hard to see. But we know that gases do exist. So these are the three states of matter. Okay, water vapor is a gas, so liquid water is a liquid, and ice cubes are a solid version of the water. So these are the three states of matter. Let us go a little deeper into the packing in solid state, and let's examine them. In solid states, the particles are tightly packed together, as you can see from the diagram here. Okay, you can see the particles are very close to one another, and they are considered very tightly packed. And if you look at the way that the particles are arranged, you will also notice that the particles are arranged in a very orderly manner, right? Maybe either one on top of the other, or in a cubic structure, or in a hexagonal close packed structure, or whatsoever, but they do have a regular arrangement. So particles are arranged in an orderly manner, and this order extends over a long range. So some people like to call it long range order. Okay, so particles are arranged in an orderly manner in solid state, and the reason why they can be arranged in such an orderly state is because the particles are held together by strong forces of attraction between them. Okay, if it is a solid metal, then of course the metallic bond keeps all the atoms of the metals together, and they are arranged in a very regular manner. So they are held together by very strong forces of attraction between them, and that's the reason why they can exist in a big number of particles, bonded together, and we can see them or feel them or touch them or whatever as solids. And there is negligible spaces between them. Of course, if they are very tightly packed together, you can see that there is very little space between one particle to the next. So there is negligible space between the particles in solid. And the particles are restrained from moving freely, okay? Because let's say one of the particle wants to move to the right, it's restrained by the other particle on the right. And if it wants to move to the left, it is restrained by a particle on the left. If it wants to move up or down, it's also restrained by the other particles in the neighboring vicinity. So the particles are restrained from moving freely. So this particle, which is somewhere in the middle, cannot go to the top because there are many other particles that is blocking its position, right? So they are restrained from moving freely. And however, it's not that they are going to stay still, but they can only vibrate about their fixed positions. As you can see in the animation here, they can just vibrate about their fixed position. Their mean positions is still going to remain the same, but they can only move left, right, up, down, or whatever, right? They can only vibrate about their fixed positions. Since large number of particles are packed per unit volume, so when we want to compare density, we always have to take the same volumes and compare. So per unit volume, maybe you can take 1 cubic meter or whatever, and you count the number of particles in solid state. What you're going to realize is there's going to be a huge number of particles in the solid. So since large number of particles are packed per unit volume, so obviously solids will have very high density, because more particles, greater would be the mass, and of course the greater would be the mass, the greater would be the density. So hence a solid having a lot of particles packed per unit volume naturally have very high density. And solid is incompressible, okay? We cannot squeeze the solids because there is no space between the particles, because they are already very tightly bonded together, right? You cannot take a piece of iron and try to squeeze, or a piece of wood and try to squeeze, or a piece of ice cube and try to squeeze. Okay, we can't compress them, right? Because if you want to compress them, means you are physically talking about moving the particles closer together. And since the particles in solid states have negligible spaces between them, it is not possible for you to compress the particles. So solids remain incompressible because there is no space between the particles to accommodate the compression. So these are the properties of the particles in solid state and their packing. So solids also have fixed shape, okay? So they don't take the shape of the container, they are just fixed due to the tight packing of the particles. They cannot move, they cannot slide or whatever, so they will be bonded together as one single cluster of particles together, and that gives them the fixed shape due to the tight packing of the particles. Let us now examine liquids, okay? Packing in liquid states. In liquid states, the particles are still relatively closer together, and since they are close together, and that's why we can see liquids like liquid water or whatever, right? So in liquids also the particles are considered close together. And however, if you look at the particles, they are not as orderly arranged as what we witnessed in solid state. So the particles in liquid states do not have an orderly arrangement, or we call it they have a short range order. And the particles in liquid states are still held together by some weak forces of attraction between them, okay, such as van der Waals forces or hydrogen bonds or whatever. So one particle is attracted to another particle still, and they are held together by weak forces of attraction between them, and that's what makes them stay together, and we are still able to see the huge number of particles together, and that's the reason why we are able to see liquids. And however, if you look at the liquid particles, even though they don't have a proper arrangement and they are held together by weak forces, but if you look at the spaces between one particle to the next, there is negligible space between the particles. There isn't much space between the particles. And why is this property important? Because this would actually help to explain why liquids are not compressible as well. Okay, how about the movement of the particles? The particles can slide over each other, okay? As you can see in this animation here, the particles can slide past one another. Unlike in solids they could only vibrate about their fixed position. However, in liquids, they are able to slide over each other, and that's what gives them the ability to do pour, right? Since large number of particles are packed per unit volume, relatively still, liquids have higher density, okay, compared to gases, because gases, if we were to take the same volume and we count the number of particles in gaseous state, we're going to find very few particles, but still for liquids there is a relatively a large number of particles packed within the same volume, and therefore liquids also have higher density compared to gases, okay, but not nearly as high density as the solids though. Liquids do not have fixed shape, okay, they do not have fixed shape. Since the particles can slide over each other, so they're not going to just stay in one place. So the moment you pour it into a container, they're going to slide over each other and they're going to just settle down and take the shape of the container, and therefore liquids do not have fixed shape. Now let's look at the gaseous state and what is the packing in the gaseous state. In gaseous state, the particles are very far apart, okay, they are extremely far away from each other. So this is a diagram of a particle in gaseous state, okay. You can see within the same volume we can find relatively very few gaseous particles. So the particles definitely do not have an orderly arrangement, they are randomly arranged, right, but they will fill up the entire space, but they don't have any order of arrangement, they have disorderly arrangement or do not have orderly arrangement. The particles have very little or no force of attraction between them. In fact, one of the particles will never know the existence of the other particle until and unless they collide with one another. So otherwise they are not even aware of the other particles present, okay, and there is no force of attraction between the particles in gases. And as you can see from the diagram here, there is a lot of space between one particle to the next. There's a lot of space between the particles. And that's the reason why if we can apply a force, okay, to a gas, of course the particles can be moved much closer together, and that is the reason why gases are compressible. And the particles have complete freedom of movement, okay. As we can see, there's huge space between them and they can move freely, okay. They are not like restrained like in solids where the particle is restrained from the neighboring particles from moving freely. But however, in gaseous states there is huge space, so the particles can move as they wish, right? So they have complete freedom of movement. And also you take note that the particles in gaseous states have a higher speed. They move at a very high speed or velocity. So their relative movement is going to be much faster compared to the speed of liquids or speed of particles in solids. Since very few particles are packed per unit volume, within this volume you can see only a few pieces or few particles, the gases have extremely low density, okay, and that's one of the reasons why gases tend to rise, okay. They have a low density. Gases are compressible because there is a lot of space between the particles. So if one particle is further away from another particle, of course we can push them closer together, and that's what we mean by compressible. Gases are compressible, highly compressible, because there is a lot of space between the particles. And gases, like the liquids, they do not have fixed shape. Because they don't have a fixed shape, because there is no force of attraction between the particles, right? As force between the particles is negligible, so there is no necessity for the particles in gaseous states to have a fixed shape. So the particles are free to move and they will not have the fixed shape. Okay, now let's examine the relationship between temperature and the speed of the particles. The temperature is an indication of the kinetic energy of the particles in the body. Okay, kinetic energy means the energy that a body or a particle possess due to the motion or due to its speed. So temperature gives us a good indication of the kinetic energy. Of course, the higher the kinetic energy of the particle, the higher the speed of the particle is going to be, and of course the higher the speed of the particle, the temperature is going to be higher. So if we were to look at the particles at a particular temperature, at lower temperature the particles have, okay, lower amount of kinetic energy. As you can see, the particles are moving quite slowly. Okay, they have a lower kinetic energy and they move at relatively a low speed. Okay, and what would happen if we go to this and, you know, if we were to actually start giving them more kinetic energy from the heat energy? So at higher temperature, if we were to increase the temperature, let's say we start heating the, you know, the substance, and as we heat, the temperature goes up, okay, then of course the heat energy is going to be converted into kinetic energy of the particles, and the particles will now begin to have higher amount of kinetic energy, and of course that kinetic energy will translate to higher speed. So the higher the temperature, the particles move at much higher speed. The lower the temperature, the particles move at lower speed. So the temperature is directly is indicative of the amount of kinetic energy that the particles in a particular state possess. Let us now look at change of states, right? So solids, as we remember, solids have tight packing and they vibrate about their fixed positions, and you can see in this diagram, this is solids. And when particles in solids gain sufficient energy to break the bonds holding them together in the solid state, they will convert into liquid state, or they will become, or they will move into a liquid state. So the process of changing from solid to liquid, we call them as, or it is called melting. Okay, when solids turn into liquids, okay, by breaking the bonds holding them together in the solid state, okay, all these tight bonds, if it is broken, and they can slide over each other with weaker forces of attraction between them, that's when we call them liquids, right? So if the process of changing this and breaking the bonds and converting into this, okay, into liquids, is what we call as melting. Now when particles in the liquid state can also gain energy, and if the energy is sufficiently large, okay, it can break the bonds holding them together in the liquid state, and they can change into gaseous particles with complete freedom of movement, right? And this process of changing from liquid to gas is what we call as vaporization, or it's also known as evaporation. So evaporation is a state change from liquid state to gaseous state. How about if you want to go the other way around? Okay, what happens when particles lose energy? When particles of gases, okay, here the gases, if they lose energy, so of course when they lose energy, they're going to move much slower. When they move much slower, they're going to move closer to each other, and when they move closer to each other, they're going to form the bonds. And when they start to form the bonds, that means they're going to be attracted to each other, okay, and they're going to enter into liquid state. The process of changing from gaseous state to liquid state is what we call as condensation. If gases, okay, become liquid, such as, you know, water vapor condensing on a glass to turn into liquid water, is called condensation. Now how about, can liquids become solid? When particles of liquids lose energy, right, if the liquid particles are going to lose energy and they're going to move much slower, they're going to get into a more regular arrangement of the particles, and of course from liquids they're going to change into solids. So when the process of changing from liquid to solid is what we call as freezing. Okay, the liquids becoming solid is called freezing. Now how about, is it possible for solids to become gases directly, or gases to become solids? Of course it can. Some solid particles, okay, from this can gain sufficient amount of energy to break away from solid state and go directly into gaseous state without going through, you know, the melting process and evaporation process. That means without going through the liquid state. When it can go directly from solid state to gaseous state, we call that process as sublimation. The process of changing directly from solid to gas without going through the liquid state is what we call as sublimation. One example of sublimation from solid state to gaseous state would be, you know, mothballs. Okay, of course you would have seen some mothballs brought into the room or placed in your cupboards or in your toilets or whatever. You would have seen the solid state of the mothball or the naphthalene ball, but you would have never seen the liquid version of it, but you would be able to smell the naphthalene ball smell, right? That is because the naphthalene ball is directly changing from solid to gas, okay, and that process is called sublimation. Another good example would be ammonium chloride. If we were to heat up ammonium chloride, it's going to change directly into ammonia vapor and hydrogen chloride vapor, and then when it comes into contact with some cold surface, they will reform the ammonium chloride. So we would also say ammonium chloride sublimes. And another one good example of sublimation would be if we were to heat up some iodine, solid iodine crystals, they will turn into nice beautiful purple vapor. So that's another example of sublimation. Now what about if we go from gaseous state to solid states directly without going through the liquid state? Yes, it is possible. Like for instance, the frost in the refrigerator, okay, or in the freezing compartment of the refrigerator is a very good example of water vapor turning directly to ice without going through the liquid state. When the water vapor comes into contact with the very cold surfaces of the refrigerator freezing compartment, they lose so much of energy and they suddenly turn into the ice, right? And that is what we call as the frost. So the process of changing directly from gas to solid without going through the liquid state, okay, without having to go through the liquid state, is also called sublimation. So sublimation is the state change from solid directly to gas or vice versa without going through the liquid state. Let's look at what happens when we supply energy to any matter or any substance. The energy can be used for two of the purposes, okay, in either or fashion. So the energy can either be used to increase the kinetic energy of the particles, okay, the movement energy or the kinetic energy of the particle. So if we supply heat energy, it goes into increasing the kinetic energy of the particles in that matter or in that substance. Or alternatively, the energy can be used for breaking the bonds holding the particles together in a given state. So either it can go to increase the kinetic energy or it can go to breaking the bonds holding the particles together in that particular state. So increasing the kinetic energy, what it does, of course, when it has a higher kinetic energy, it's going to increase the speed. And as we have seen earlier, right, when the speed becomes greater, the temperature also becomes greater, because temperature is an indication of the speed of the molecules, or the speed of the molecule is an indication of the temperature, right? So when we increase the kinetic energy, the increase is converted into higher speed of the molecules or the particles, and this in turn would increase the temperature, right? Unless we stop increasing the kinetic energy, the temperature would remain constant. So increasing the kinetic energy increases the speed of the particles and hence the temperature of the substance. So during bond breaking, that means if we go the other way around, if let's say we are breaking the bonds holding the particles together in a given state, the kinetic energy or the speed or the temperature of the substance remain constant. Okay, why would that be? Because we are not using the energy to increase the kinetic energy, we are using the energy to break the bonds, right? So obviously throughout the process of breaking bonds, the kinetic energy is not going to increase or decrease, so it's going to remain the same. Of course, when the kinetic energy is going to remain the same, the speed is going to remain the same, and of course the temperature would also remain the same. That's what I mean by during the bond breaking, the kinetic energy, the speed, as well as the temperature remain constant, since the energy is used now to break the bonds holding the particles together in the given state. So okay, this increase in kinetic energy or increase in speed and temperature happens when the particles or when the substance is in the same state. That means within the solid state to solid state, or within liquid to liquid, or within gas to gas, right? So that is what is going to happen here, and that's the reason why within a same state there would be an increase or decrease in temperature can be observed. But however, the breaking of the bonds, right, is necessary when we want to change the matter from one state to another. So the bond breaking happens during the change of state or state change, right? So only during the change of state from solid to liquid or liquid to gas or whatever, then we need to break the bonds, and of course the energy would be utilized to break the bonds, and that's why breaking bonds happens only during change of state. When the temperature is plotted against the time of supplying the energy or directly as a function of the energy itself, the following heating curve can be obtained. So what would be a heating curve? Of course, we're going to plot the temperature on the vertical axis against the time of heating. So let's say we use a constant power heater, and of course the longer the time, there is more energy being supplied. Okay, so let's see what happens. So if let's say a particular substance is in a solid state and we supply the energy is going to go into increasing the kinetic energy of the particles, and of course this in turn would increase the speed. Of course, when speed increases, the temperature is going to go up. So as we can see from this graph, the temperature is going to go up all the way, and of course once the particles are already vibrating at the maximum speed, so the maximum speed in solid state is obtained. So with the bonds still intact, the particles cannot vibrate anything higher than that speed. So already it has reached the maximum speed in the solid state, and the temperature will stop rising because the speed of the particle will remain constant. So now what happens if you do not stop supplying the energy as the time proceeds? The energy would now be used for breaking the bonds. Okay, the energy would now be used for breaking the bonds, holding the particles together in the solid state. So the speed of the particles throughout remain unchanged because the energy is now no longer used to increase the kinetic energy or increase the speed or the temperature, and that's the reason during bond breaking the speed of the particles remain unchanged. Of course, if the speed of the particle remain unchanged, then we're going to observe that temperature throughout the state change process is not going to increase or decrease. It's going to remain constant, and it is going to be a horizontal line. The temperature is not going to change. It's not going to increase. It's not going to decrease. So speed of the particles remain unchanged for this part. And of course here the first bond started breaking, right? Okay, and this is exactly the position when the last bond in the solid state is broken. Okay, so here is the first bond in solid state starts breaking, and then breaks more and more, and finally all the bonds or the last bond in solid state is broken. And of course, since all the bonds are broken, the particles, okay, do not have that orderly arrangement. They are able to move a bit more freely. Okay, they can slide over each other and all that. And what happens if we do not stop supplying the energy? So the energy is now going to increase the kinetic energy once again, and of course this in turn is going to increase the speed as well as the temperature, and that's the reason why you can see the temperature of the substance begins to go up because of the increase in the speed, which is due to the increase in kinetic energy, which is due to the energy that we supplied. And what happens again, with the bonds still being intact, once again there is a limit, right, to the maximum speed of the particles in the liquid state. So maximum speed of the particles in the liquid state is reached at this point, and of course no matter how much energy we try to give, with the bonds still being intact, the particles cannot move any faster than what it already is moving. So it's already at the maximum speed in the liquid state. And if we continue to supply the energy, this time the energy is going to go and break the bonds holding the particles together in the liquid state. So obviously the first bond in the liquid state starts breaking here, and the last bond in the liquid state is broken right at the end of this line. So throughout this process the temperature remained constant because we were channeling the energy to breaking the bonds and not into increasing the kinetic energy or increasing the temperature. So this is the position at which the last bond in the liquid state is broken. And if we continue to supply energy, once again, of course, there is no longer necessary for you to break the bonds because all the bonds in the liquid state has already been broken. And now the particles have greater freedom of movement, and they are already in a gaseous state. And obviously, we will keep increasing the kinetic energy, which will in turn keep increasing the speed as well as the temperature, and the temperature begins to rise once more, right? So this is typically how a heating curve of a pure substance would look like. So if you were to take water and if you were to perform this experiment, or continuous heating, and if you were to record the temperatures, and this is exactly how the temperature of the water as it moves from ice to becoming water vapor, this is how the temperature will look like. So of course here the particles are in solid state, okay, so throughout. So here only the speeds kept increasing until it reached the maximum speed, so it couldn't vibrate any further, and the energy was now channeled into breaking the bonds in the solid states together, and then it will enter, all the bonds in the solid states are broken, and the particle now enters into the liquid state here, and then once again it reaches the maximum speed with that bond in the liquid state, and then the one by one all the bonds are going to be broken. So once again we're going to break all the bonds holding the particles together in the liquid state. Last bond in the liquid state is broken, and the particle then enters into the gaseous states. So these are the three typical zones that we will see in a typical heating curves, right? And what is this temperature at which the solid, okay, this is how a typical heating curve of a pure substance would look like. What is the temperature at which the solid turns into liquid? Okay, that temperature is what we call as the melting point. So remember, throughout the melting process, the temperature is not supposed to increase or decrease, but remain unchanged if the substance is pure. The temperature at which the liquid changes into a vapor or the gas, that temperature is what we call as the boiling point, okay, or you can call it vaporization point also. So these are the two temperatures that is indicated by the typical heating curve of a pure substance. Now take note, at this point all the particles are still solid, the melting hasn't started, and then as the process goes on, as we keep supplying the energy, it will move all the way until every particle has already broken the bonds, and every particle has entered into liquid state. So at this point all particles, I mean the entire substance is completely a liquid, and of course in between, okay, here to here we're going to have a mixture of solids as well as liquids, and the same thing can be applied for the gas liquid transition. So at this point every particle is liquid, so all of the particles are liquids, and of course as we reach the end of this point here, all the particles have already entered into gaseous state. Every bond in the liquid state has already been broken, so all the particles now have freedom of movement, so all become gaseous particles, and of course in between is where we get a mixture of liquids and gases. And of course the name given to the process, right, if solid turns into liquid, okay, it's called melting. So if we go this way from solid to liquid state, we call the process as melting. And if we go in the opposite direction, that means liquid becoming solid, is what we call as the freezing. And here if we change from liquid state to gaseous state, we call it evaporation or vaporization. The reverse of the gas, the reverse of this process is what we call as condensation, where gas turns to liquid. So this is called condensation. So how about the cooling curve of a pure substance? It is exactly similar to the heating curve, but however this will have a negative slope. Of course we are cooling down, that means the temperature is supposed to drop as we move from the gaseous state into liquid state into solid state, and the temperature at which gas to liquid transition happens is called boiling point. Liquid to solid transition temperature is called the melting point. So melting point can also be called the freezing point. So this is how a typical cooling curve of a pure substance looks like. That brings us to the end of solids, liquids and gases. Hope you have enjoyed the lesson. Till I see you next time, have a great day.